Good morning. It's December the 7th, 2014. Why am I giving you the date? Well, I might use this video again. And the reason I'm here this morning, I'm here to help my students prepare for a final examination in basic electricity. Of course, the rest of you YouTubers are welcome to get what benefits you might from this lecture. Now, we're going to start off. These are formulas that were written for parallel circuits, and there are certain things I need to point out. For those who have never had this course before, who don't understand parallel circuits, notice here that these two symbols are in parallel, aren't they? So this is a sign for parallel circuits. Now, we have a 3K ohm resistor, and we have a 5K ohm resistor in parallel. Now, I'm going to demonstrate very shortly how to solve that problem. But notice also that we have a 10K ohm resistor in series, now notice in series with the 3K and the 5K, which are in parallel. And the circuit will look like this. What we have, this circuit is drawn, this is ground, and this is the parallel circuit. It's a 5K ohm resistor and a 3K ohm resistor. Now notice we're going to combine these two together, and we're going to get something less than 5K, because in a parallel circuit, the largest, or the sum, is going to be smaller than the largest resistor. I hope you understand that. Some of you may not know that yet, but the people in my class do. And that would be a good thing for you to memorize if you're a YouTuber and you take an examination in the future, whether it's on your school or some formal FCC exam or a ham radio license. But just remember this, that the sum of 3K and 5K in parallel is going to be less than the 5K. Now notice, where these two come together, we have something called a node. And the current entering the node here is going to split, and it's going to split up to the 5K. And what it's going to do, what it's going to be dependent upon, is the resistance. Ohm's law will hold in these two cases. Now, a little later, I'm going to give you a voltage divider formula, and I'm going to give you a current divider formula. And in this case, we're talking about the current dividing. Okay, these two currents flow up to this node, and then it enters this resistor that's in series with the two parallel resistors. That's why it's called a series parallel circuit. Now, the current through the series resistor here is going to be the total of these two currents going through the parallel circuit. They combine here, and then this series circuit will have the sum of those two components of current. Now, something else I want you to remember. I want you to remember that if you have a resistor here that's a 10K or any size resistor, and you get an answer that's less than 10K in this case, then it's going to be wrong, because what you're doing, you're adding resistors in series, and resistors in series are R total equals R1 plus R2 to Rn. And as a consequence, you can see that you're going to have something added to this 10K. And if in fact you get a total RT less than 10K, then in fact that problem needs to be reworked. Now, let me recommend to you, if you have time on an examination, to always work these problems twice. No one's going to do these problems longhand. The great majority of people will use a calculator. In my class, I recommend a TI-30XA. And that's a great little calculator that only costs $8.95. And for a technician, This will work almost any problem that you have. And it's also great in physics in the electrical section for non-engineering students. If you're an engineering student, then you probably need to go to a TI-84 at least. But we'll talk about that another time. I'm not here to sell calculators today. What I'm here to do is summarize the semester using Chapter 6 in order to prepare you, the students, for the final exam. Okay, now with that said, what formula are we going to use to solve the parallel section? Well, there's several methods, but what I'm going to use is what's called the reciprocal method. And that's 1 over R1 plus 1 over R2 plus 1 over R to the nth. And when I say R to the nth, I'm meaning that you can go totally out to the right, stringing as many parallel resistors in there as you have. You may not just have 2 resistors, you may have 20. And this formula will work for both of them. Now normally, the normal convention is write RT right here. RT equals. Let me divide that a little bit so it's not confused. So this is a formula I would use, but you can also use something called the product over the sum if you only have 2 resistors. Now this is only good for 2 resistors. Okay, what do you mean by the product? I mean by the product R1 times R2 over R1 plus R2. But like I've recommended in my class, why not just pick one of these formulas that you know very well and put these on your calculator? It's so easy to do. And this is only good, this RT product over the sum, is only good for the I'm sorry, let me back up. The product over the sum is only good for 2 resistors. Now, we're going to make this problem number 1. And what we're going to do, we're going to solve for this problem. Now, those of you who have the TI-30XA, and I'm hoping that TI will see that I'm selling calculators for them, and send me a bunch so I can give them to my students. Do you hear me, TI? Listen to me, TI. I'm just joking. I hope you realize. But you want to send them, go ahead. Okay, to set up my calculator, to work scientific notation, and that's what we're going to use here, scientific notation, I hit the second. Okay, and then I hit what? You students know what it is. I hit the scientific notation. Now look what showed up in the window up here. Oh, you can't see it, can you? So I'm going to scoot it over. Unfortunately, this old machine here doesn't give me much leeway. There's not much surface. Okay, now that I've got that set up. Now, here in my class, I'm only going to use 2 significant digits. So we want to set our calculator to have just 2 significant digits. Now, if you're using another calculator, for example, if you're using a TI-83 Plus or any other instrument, what you do, you hit, in this case, you hit the second, and then you hit the fix, which is right here, and I want it at 2 places, so I hit the 2. Now, notice now that I have the digits showing up in the window to 2 significant numbers. Okay, now, to solve this problem, what am I going to do? Okay, I'm going to move the calculator aside. I know that you know how to hit the keys, so I'm not going to demonstrate that. So what we are going to look at, though, we're going to solve this problem. Now, the first thing we want to do, we want to solve the parallel part of it first. So I say that 3K in parallel with 5K is how much? Okay, I'm going to go ahead and put this into my calculator. You do the same thing. So I put in 3, then double E in this case on this calculator, double E, 3, reciprocal, plus 5, double E, 3, equals, and then I hit the reciprocal again. And let me do that again. I know that's not right. And that's one thing you have to do. You have to look on your calculator, and you have to decide when something seems wrong. Because if it seems wrong, it probably is. Now, I punched that into my calculator, and this is what I came out with. I came out with 1.88 times 10 to the third. Now, some of you say, or would quote this as 1.88 with raised to the third power. Okay, now let's go ahead and look up here at the formula. We have a 10K in series with the 5K and the 3K. So we're going to add that then. We're going to add the 10K, and it's pretty obvious what you're going to come out with. You're going to come out with 11.88 times 10 to the third. Now, as you know, 11.88 times 10 to the third is, in fact, in metric notation, 11.88 kiloohms. So, this is a right number, but that's not the right answer when you have 11.88 times 10 to the third. You need to change it into K or meg, and I've taught all of you how to do that, and I hope you remember. If you can't remember how to do that, though, leave this answer here, 11.88 times 10 to the third. You'll get partial credit. Now, what I want to do is work a little different kind of problem, and then I'll end this type of situation here. What we're going to do now is work one of the other problems that I gave you as practice. Now, let's look at this. Let's look at number 9. Okay, number 9 is 9 ohms plus 10 ohms plus 2 parallel resistors, 20 and 30 ohms. Now, I'm going to write that, and I'm going to redraw it in a moment. So what we have 9 ohms plus 10 ohms plus 20 ohms that's in parallel with 30 ohms. Now, the first thing I want to do is draw a circuit, and here's what I have. Now, you don't need to necessarily draw these circuits if you know what you're doing, but it might help you to visualize what you actually have. Now, we start off here. You have a 9 ohm that's in series, and you have a 10 ohm that's in series. And here you have a 20 ohm, and you have a 30 ohm. Okay, let me scoot that up so you can see it now. So let me reiterate what I just said. Okay, I have a 9 ohm in series. I have a 10 ohm in series. I have a 20 ohm in parallel with a 30 ohm resistor. Now, I'm going to rewrite this formula that we've developed, and I'm going to say this, that I combine these two together. I put 9 plus 10, and that equals 19. Now, I'm going to work the parallel. Some people want you to work the parallel first, and that's probably the best thing to do. But I've already done this, so let's go ahead now and work the parallel part of it. Okay, I have 20 ohms in parallel with 30. Go to your calculator. Are you ready? I'm going to clear my calculator, and I'm going to make sure that I'm still in scientific notation. So I have a 20 ohms, so it's 20, and I take the reciprocal of that, plus 30 ohms, and I take the reciprocal of that, and that equals. Now we hit the reciprocal again. I came out with 12 ohms. And does that make sense? No, it doesn't, does it? No, maybe it does. I'm joking with you. Let's go ahead and put down 12 ohms. Actually, what it came out to be is 1.20 times 10 to the first, and we're going to convert that here shortly, but not till we finish the problem. Okay, now what we're looking at the combination of these two together, which is 19 ohms. That's going to be RT equals 19 ohms plus 12 ohms. And let's count on our fingers, but I'd prefer you count on your calculator. Do you get 21 for that? 21 ohms? Now the best thing you can do for yourself is run this through again. And I'm going to run it through my calculator again while you do. Now, I've advised my students, let me move this so you can see it. This is hard to do on this particular machine. I've advised my students, even when you have simple numbers like this, when you're on an examination, put them into the calculator. Now, it's quite obvious here that 19 and 12 are not 21, are they? 19 and 12 is 31. So, run your problems through the calculator. Now, I've finished that type of problem, and you'll probably see some of these real soon, probably about Tuesday. It may be these, but it may be ones like them. You need to know how to work them. So if you don't understand it, go ahead and work these, and I'm available till 6 o'clock tonight, but not past 6 o'clock. I know that many of you have many things that you have to do with your life, but I've got a few things myself, and I'm available for any kind of questions before 6 o'clock tonight. I was available for an hour after each and every class, and some of you took advantage of it, and I know that those people, I've seen them work these problems, they're going to do well. But I also say that you can learn this on your own with the textbook. And I advise you to spend some time in the next couple of days working problems like this. Don't try to memorize answers, because I may change the numbers, and you'll get them wrong if you put down memorize answers. Okay, I'm going to go ahead and move on to something else now. Now, the next kind of problem that I want to talk about is something called a voltage divider. And let's go something like this. Okay, what we're going to do with this voltage divider, we're not going to use Ohm's law. We're going to use a variation of Ohm's law. And what we're going to do is use something called the voltage divider formula. And that formula is this, that any voltage, Vx we'll call it, is equal to what? Is equal to Rx divided by RT. So it's quite obvious what you're going to have to do to solve this problem. We're going to use some simple numbers, but we could have used larger numbers, and you very well might see those on a different piece of paper here Tuesday. Now, what we're looking at, let's just call this 40 ohms. Let's call this 100 ohms. Let's call this 1,000 ohms. And let's call this one, let's make it 20,000 ohms, just to see a big difference. Okay, now what we're going to want to do is decide how to solve this problem first off. Now, looking at this, what you could do, you could add all these resistors together, and you could get RT. And I'm not going to do that. I'm going to let you do that. But you could add them all together, and you could get RT. Now, then you could find the current, couldn't you? Because I equals what? V over R, and we're talking about totals, that I total equals V total over R total. Now some of you use this that I equals E over R. Now remember we discussed that? In our lab manual, that's the formula that's used. But in our textbook, it's I equals V over R. So either one's correct. We're not worried about which one you use, just so that you know how to present the problem. Now, you could use that. You could decide the current through the circuit because you know what E is. E total is 300, and you can add up R total. Somebody do that real fast in your head. Let me think about that. Okay, let's look at that closely. I have 20K and I have 1K, so that's 21K. I have another 100 and then I have a 40. Now, what is that? Isn't that about 2.11 times 10 to the fourth? 2.11 times 10 to the fourth. Well, that is a good number, but let me put that in my calculator. Hold on, let me make sure I'm right. Remember we discussed that? Don't add these up in your head. Put them into your calculator. Okay, so now looking at that, I want to put this into the metric format. So how do I do that? I need a 3 here, 10 to the third, because we want this to be in K. So what I have to do, I have to move the decimal point one spot, correct? I have 21.1 K ohms. So that's RT. So RT equals 21.1 K ohms. Now, what's the voltage? Well, look up here. There it is, right there. It's our V total. Some people say VS, V source, V total, same thing. So I'm going to say that the V total is 300 volts. Now, like I say, now we could figure the current, but we don't need to do that, do we? Because we're going to use the voltage divider formula. Now, what is the voltage divider formula? What's that all about? Let's go ahead, you and I, and develop that together. We said it's Vx, okay, equals Rx over RT. Well, we know we're going to use that formula here, and we're going to say that, oh, wait a minute, let me add something to that, times V total. There we go. Now, am I losing sound? There, I've got it back, but I don't hear it. I hope that you're hearing it, because I hate to go on and not be able to record this. So here we go. Okay, let's go ahead and use the voltage divider formula. I hope my sound is back. I'm going to go through this, and hopefully I won't have to do this thing again. Now, what we need to do is develop a formula. Now we know RT. RT is right here. And we know VT. So if I look at this circuit, I know that the total voltage is going to be a fraction. This 40 here, which we're going to call Rx. Here's the formula we're using. We're going to call this Rx, but it's no longer X, is it? Now it's a 40 ohm resistor. And it's over RT. And RT is 21.1 K ohms. Times, don't forget the times, it's easy to leave it off. Now we're looking for VT right now. Times total voltage, VT, which is right here. This is total voltage. Times 300 volts equals. Now you can see that this 40 ohms is only part of RT, isn't it? So now we can go down, if we're solving voltage divider formulas, we can develop the formulas and then we can punch them into our calculator. Okay, we're going to use this formula here, Rx. In this case, the 100 is Rx, the 100 ohms, divided by RT, and RT we figured out was 21.1K. Now, for your knowledge, it's always going to be, in this formula, it's going to be 21.1K, 21.1K, so you can go right down the line, 21.1K. And the Rx, of course, is going to be the resistor under consideration. In this case, it's 20K, isn't it? In this case, it's how much? 1K, or 1,000 ohms. And in this case, we've already put it down, and those are going to equal. Now, I'm not going to solve these. I want you to solve these. But what you're going to end up with, you're going to end up with a total voltage. Now, when you finally put the voltage across VR1 plus VR2 plus VR3 plus VR4, that's going to equal to VT, which in this case is 300 volts. If you don't get, by adding those voltages drops against these resistors, if you don't get the total voltage here, then you've done something wrong, and you probably should go back and try it again. Okay, that's just a matter now of punching these into your calculator and moving on to the next problem. Now, let me stop for a minute, and I need a drink of water. Now, using this diagram, and we could have used any diagram that's of a series parallel circuit, we're going to discuss some of the facts about resistors in parallel and resistors in series and resistors in series parallel. Let's just discuss some of these facts. Here's one of the facts. If two resistors are in parallel, they're going to drop the same voltage, aren't they? So if I have a 5 volt drop across here, I'm going to have a 5 volt drop across here. Why? Because they're the same wires. Now the resistors together are not, the resistors by themselves are not going to drop. They're not going to drop the same voltage. But when they're put in parallel, they will. Because remember, these two resistors here are acting as a single resistor to drop the voltage. And like I was saying, if you measure 5 volts on this one, you're going to measure 5 volts on this one. Now, in a series parallel circuit, it's going to consist of resistors in parallel and resistors in series. That's what we're talking about when we're talking about a series parallel circuit. These two resistors here are in parallel, and they're in series with this 10K ohm resistor. So in a series parallel circuit, it's going to consist of resistors in both series and parallel. Now, let's take a negative approach to this. Let's say that no problems could exist if you had two 10 volt sources. I'm sorry, let me reiterate. If you had a 5 volt source in parallel with a 20 volt source, would you be able to have current flow? Would it be able? Yes, you'd have current flow, but it would flow to the other battery. It would flow to the battery with the least voltage. In other words, if you had the 20 in one and 5 in the other, current's going to flow to try to charge that 5 volt battery. Now, with that said, if you're ever presented with a view, would it cause a problem if you hook up two batteries in parallel? Now, note parallel. Series is no problem. But when they're in parallel, if you hook up two of them together of different voltages, one is going to flow into the other battery, and as a consequence, you're going to have a problem. Simple as that. Okay, let's go on. Now, we want to talk about something called a loaded voltage. A loaded voltage divider. And we had a voltage divider here. Let me get it. This is our voltage divider. Now, the purpose of a voltage divider, of course, is to tap off different voltages. So what we could do, we could come out here with what's called a load. Now anything we put out here is going to be a load. This could be a light bulb, it could be a resistor, or it could be a motor. Now take a minute and think about that. We have a certain voltage drop across here. Now, if I put another resistor in there though, that's going to make these in parallel, isn't it? It's going to be in parallel with the load. So what's going to happen? This is going to become, this series circuit is going to become what? It's going to become a series parallel circuit, isn't it? A loaded circuit, a loaded voltage divider is going to become a series parallel. Before it was just a series, but now it's a series parallel. And if you have two or more resistors connected in series, they do form a voltage divider, don't they? Because you're going to, when you figure these out, you're going to see that you have a voltage here of a certain volt, a voltage here of a certain voltage, a voltage here of a certain voltage. So two or more resistors connected in series do form something called a voltage divider. Now if two resistors are in parallel, are they going to carry the same current? Is this going to carry the same current? Both of them? No, they're not. The current is going to be determined by what? It's going to be determined by the resistance of the parallel resistors. For example, if this were a 20K and this were a 30K, the lower ohmic value will carry what? The most current. Now, if you have a voltmeter and you connected it across the component, can it be viewed as being a resistor in series with that component? No, it can't, can it? Because a voltmeter is in shunt, or it's in parallel. So a voltmeter, when it's connected to a component, we don't connect a voltmeter in series. We connect it in parallel, or shunt. Now, we're not going to talk about a bridge circuit too much right now. We're going to go ahead and leave that up to you, and we'll have a few more questions in a few moments on it. But you should go ahead and study the bridge circuit. And you can see quite readily, if you're looking in the book at the bridge circuit, that not all the resistors have to be the same to make it balanced. So in other words, let me make a drawing. Maybe that'll clarify it a little bit. I'm going to just turn this over. Here we have a bridge circuit. Okay, do you recognize that as a bridge circuit? We're going to call this R1, R2, R3, and R4. Okay, now it doesn't matter what the size resistors are here as long as they have the same voltage at this point here and at this point here. If in fact you have the same voltage here and the same voltage here, then you're going to have 0 volts using a galvanometer. You're going to have 0 volts across there. And that's a G for galvanometer. So looking at that circuit, these resistors could be different values. And what we're doing, let me redraw that circuit for you. I'm not going to take the time to make this beautiful. I think you do know exactly what I'm doing here. Okay. Now looking at this is R1, R2, this is R3, and this is R4.